Hello everybody. Today we talk about the logic design for the large chip manufacturing. How engineer can design the entire logic of such a large chip. Well, usually multiple engineers are assigned for each partitioned area and design each area and later put them together into a single chip. Okay, that's a typical approach. First of all, you need to understand logic design. Use the ESD, electronic design system, support so-called logic design using this type of diagram on the screen. You construct the logic, and once you construct, you make it a module, and you put the module together, right? And the module together, you design a larger unit, and you keep increasing the size to the entire partition you are assigned. Okay. Another one is using HDL. What HDL? Hardware description language. Hardware description language is like a programming like language, and when you write the logic using that programming language, it's translated into this kind of logic. During this translation, certain amount of optimization is done, but it's not clear how much it does optimization. I give you an example. Usually this is very useful tool to design the random logic. Random logic is like in the CPU or GPU. It often shows up in the instruction decoding and control logic. Now, for example, instruction, suppose add A, B is like this opcode is like 1001 whatever 16-bit, and another 8-bit is for register address. So this 16-bit, what you do is, this is on, next bit is inverted, keep going 16-bit. When all the bit match up, this end, huge end, 16-bit end, then this you realize add instruction came. So all the instruction sub or multiply whatever the opcode is decoded by random logic, and when you put together, it's compile this software language into logic. Excuse me, logic. Then it's decode all the instructions. But this instruction, for example, the add, sub, multiply, those only controlled by, say, 4-bit here. The 12-bit is the same. It's better to have a 12-bit decoded by AND gate and use this one to secondary decode into add, subtract, multiply, shift, whatever. Okay, so this way you reduce the amount of logic. Usually the instruction unit is not time critical, so you have plenty of time. There's an extra stage, two stage to do it, to reduce the logic. And this kind of things is human look at and do the optimization easily. But if you have like you know, like 200 instruction randomly decoded and try to optimize the logic, this compiler, it depends on this compiler, the intelligence, see how much it can come up with optimization, or it can be totally random logic here, the big unit for instruction decoder. And this is like once you have a bug, it's very hard to debug, and also not sure if it's going to be efficient or not. So you have this kind of problem to deal with using this HDL. Okay, but if you do the straight logic design, pretty much human decide all the hierarchy of the logic, and it's pretty much optimized. Now when it's come to the data path is like, okay, data path is like where the data flow, data and address flow, versus control logic, like an instruction, pipeline control, parallel calculation coordination. And this kind of logic is tend to be random, and this tend to be very regular. So this probably better use the traditional method, like for example you have multiplexer, 32-bit, and you select the path, right? So it's going to be multiplexer, this is select, this is I0, I0, I1i, and IXI. One of the element here is going to look like that. So this kind of data path, this is multiply 32. It's much easier to keep control over all the logic design using this logic diagram, and it's very visual and conceptual, visual and conceptual, so you can see where to improve much easier. But if you write it the code, software code, you probably don't know how the data flow, and it's very difficult to do that task. So actually you can combine both HDL approach and data logic diagram approach, and EDS typically support both method. You can mix it. Okay, so that's the way whole things. So the one designer is assigned to make a data path for like a memory access, and then memory control logic is going to be HDL, but the memory access, address, and data path, those can be logic diagram design. And that's the way it can be organized pretty much, because this control tend to be random logic, and random logic is very hard to understand sometimes how these things goes. This memory weight and memory full, whatever those control signal randomly come in, and very difficult to understand. Maybe the code level is easier, and try and error to compile again and again. So this is about the method of logic design. And actual logic design, typically CPU has register, and from register you have ALU, and has control here, and some come from register, depend 128 registers, or some come from memory unit and go to the result register, and that's go back to register, so it's cycle around. This is a general purpose CPU typical. In the middle they have a shifter. You have to do shift operation, and floating point you have both, one for exponent and one for mantissa. The floating point is divided into two data paths, exponent and the mantissa, and they interact each other. Like shift amount is determined by result of exponent ALU that dictate how much to shift, kind of things. So this is a typical. Now the GPU and AI has a different architecture. These architectures, you look at the logical design level, it's interesting. Each company uses a different idea, different kind of design. Not every chip is different, the same. For example, some try to utilize pipeline, some try to use more parallel. And AI and GPU, in the previous video I talk about number system determined by architect. The architect of chip determine overall design concept, and it's need to start with number system you have to use. And if number system is very small number, it's not like a 64-bit, because you don't need accuracy. For GPU and AI, accuracy is secondary. So in order to increase the speed, they tend to make a parallel, means the CPU component, like a ALU typically, make it like a 8-bit, the minimum, and you can have like 1,000 of ALU. The only problem is data doesn't come from register. They don't have that many registers, so it's come from memory. You deal with a large memory, like the matrix calculation. Matrix size is 1,000, some 1,000 by 1,000 kind of matrix. Because the GPU, you have a 3D model. 3D model is constructed by many dots, and between the dot, triangle area is rendered, give us some texture and the colors and stuff. And when you rotate this, you have to multiply the coordinate sine cosine values for the angle. The AI, this always like a face recognition, is large. The number of screen dot is going to be the size of the matrix. So matrix size is very big, but you don't need that accuracy. the dot can be gray, can be black, can be white, and you can deal with the face recognition. So parallel is preferred, but when architect emphasize pipeline, the parallel has a problem with the every computation logic need to access the memory. So, but memory access is typically just one unit access memory at a time. So this memory bandwidth become issue. Okay. So the memory bandwidth, in order to increase, say, each memory access takes 8 clock. You can have 8 leaves of memory. Means 8 memory. Each memory area can be accessed independently. Okay, and that's the way immediately you can increase the bandwidth by 8. Okay, so if you do that, then every clock you can get the data from memory. One data each clock, and that's the way those AI machine increase the memory bandwidth, make a leaves of the memories, because each memory access takes multiple clock, and it's you want to have a data every clock, one data. Okay, and if you do this, then parallel is good, but parallel can be also pipelined. How you pipeline is you get calculation data every clock, right? So it can bring it to accumulator. This accumulator. What the accumulator does is here's a multiplex. Multiplexer select which area you send the data to accumulator. Accumulator is basically you add data to the new data. So this is it's happened in the end of matrix, right? When you have a matrix Wij, and this is the X I. So it's like Wij times Xi sigma j. J equals 1 to whatever, right? So you have to, after multiply, you have to add them all. So this accumulator. So if you get the one data each clock, okay, then every clock you can add. So if you have 100, say 1000, this j goes from 1 to 1000. 1000 clock, you can finish one calculation, and you put this accumulator in parallel, several of them, so it's increase even the more bandwidth. So you can combine pipeline and this parallel calculations. Complete parallel architect has a problem with memory bandwidth. This the best way is to combine in the pipeline and parallel, so you can utilize the entire bandwidth of your memory. When you're dealing with a large matrix calculation, the memory access speed is going to be the issue. It's more issue, and also like the multiply speed. You multiply A and B and C, or you add A and B A plus B. This unit speed itself better be like 1 clock speed, but that's impossible most of the time, because like even add, here's the add. What is a typical add? Say you have 32-bit. Sometimes the carry generated. The carry goes through, propagate all the way. You know what I mean? Like 10110. Let's say 1001, whatever. So this going to get the carry. This carry is going to propagate all the way through. Okay, and this is the worst case timing of the adder. And the adder, in order to avoid that, you put the carry look ahead, and 32-bit is 8-bit each. You put the carry look ahead, the second level carry look ahead, and go through the carry out. Okay, and carry in. So it goes through at least 1, 2, 3, and 4. 4 stages of calculation to calculate this, and that can be shortened using so-called ternary logic. And this one is proposed by Russian mathematician many years ago. I read this paper and started using ternary logic, and I think engineer worked under me picked up this and probably somewhat spread in the industry, the ternary logic. What ternary logic does is there's no carry propagation. No carry propagation. That means you add A and B and you get C right away. Okay? But you pay the price because ternary, right? So each bit has 0, 0, 0, 1, 1, 0, and 1, 1 never happened. And that's a 3 different stage. That's a ternary. Using this kind of number structure, you can make a ternary logic, and if you do the add logic design, you find out it's going to be extremely fast addition. And multiplication too. Multiplication is basically you multiply. Say you have 0, 0, 1, 0, whatever, and 1, 0, 1, 0. Basically this one, and this one is added to generate the multiplication result. So it's a bunch of add. So when the add is speeding up by ternary logic, then multiplication get much faster than traditional Wallace tree architecture. Okay, so that's logic designer's job, to see what the requirement for the data path timing and how fast it has to be, this ALU, to multiply and add. Okay, and need to apply the certain, this is a trick, right? It's you use this kind of, it's not binary, it's ternary logic design. If you use that, you can speed up the computation much faster, right? So that's all logic designer's job. Okay, there are a lot more subjects, but I think video time is limited, so today we just end here, and just look for the next video.